A modern commercial airliner, fully loaded with passengers, luggage, and fuel, can weigh upwards of 400 tons. To move something that massive on the ground, vehicles rely on static friction. Tires push directly against the solid, unyielding earth to drive the machine forward. But high above the ground, this 707 is moving through a fluid medium, air. Unlike a car on a road, it has no solid surface to grip or leverage. It is suspended in a gas that resists movement rather than providing a platform for it. The only way to move forward in this environment is to exploit Newton's third law of motion. Since there is nothing to push against, the aircraft must create its own momentum by throwing mass in the opposite direction. This is the jet engine's primary function. It is a machine designed to capture atmospheric gas, concentrate it, and hurl it backward with enough force to propel the aircraft forward. This factory floor photograph reveals the industrial scale of the machinery. To process enough air to achieve flight, these components must fill a housing the size of a small van. The process begins at the intake. Giant spinning titanium blades at the front pull in hundreds of cubic meters of atmospheric air every second. Incoming airflow splits into two paths, an outer bypass path and an inner core path. Most air flows through the outer path, providing the majority of the thrust, acting like a highly efficient ducted fan. But the engine needs power to keep those front fans spinning. This power is generated by air forced into the core. Here, spinning compressor blades force this air into progressively tighter spaces, increasing its pressure stage by stage. By the time it reaches the end of the compressor, the air has been crushed into a fraction of its original volume. This causes the air temperature to rise significantly, leaving it dense and packed with potential energy. This compression is the necessary prerequisite for the engine's work. Without this density, the air cannot sustain the combustion required in the next stage. This historical photograph of an early engine exposes the combustion chambers. These heavy, reinforced units are where the dense air finally meets a spray of jet fuel. Ignition creates a continuous, roaring fire. It is not a series of timed pulses, but a constant chemical reaction. Heat from the burning fuel causes the air to rapidly expand. The highly energetic molecules demand more space. Since incoming air pressure blocks the front, expanding gases are forcefully directed toward the rear at high velocity. On their way out, these gases hit the turbine, a series of bladed discs designed to extract energy from the flow. The Russian gas spins these turbines, which are connected by a central shaft back to the front of the engine. This is the mechanical feedback loop. The exhaust powers the compressor, which in turn feeds the fire. After spinning the turbines, the remaining gases, now moving much faster than when they entered, shoot out the back. The engine uses a portion of its energy to power its own intake, while the rest of that force is used to hurl mass backward at high speeds. Look at the exhaust nozzle in operation. You can see the high-velocity gas being expelled, creating the rippling heat waves that distort the atmosphere. This high-speed backward stream is the reaction Newton described. By throwing this mass behind it, the engine generates the forward force necessary to overcome the drag of the air. This photograph of passengers boarding a BOAC Comet captures the result. These people are stepping into a cabin that remains calm and stable, separated from the thermodynamics occurring just a few meters away. Modern flight is the result of internalizing these physics. By housing a continuous explosion, we have learned how to generate momentum by pushing off of the air itself.